Alright class, welcome to video 2 on section 10.1. I want to show you a picture of a cell, a muscle cell. This is an very interesting cell. Basically, in your muscles, there are hundreds of thousands of these cells that are very, very long. And as you contract or bulge a muscle or do exercise, they contract on each other, they become smaller. But I want to point out, this cell is very, very, very long, and remember we learned that a cell, if it gets too big, its DNA has a hard time keeping up. Well, one way God has designed us, in this case, is to make a cell with many, many nucleus. Want to see all the different nucleuses? The reason God has made this cell with many nucleus is because it has to be a big cell so it can do a lot of work. It has to be big so it can contract and help you move your body. So instead of making many, many different cells, God has made one big cell where there's many nucleuses. Anyway, most cells, however, don't do that. We're going to learn about another reason why they don't become huge, like muscle cells. And that is the ratio of surface area to volume. Imagine that a cell that is shaped like a cube, like those in figure 10.2. Okay, where's figure 10.2? Hold on. Just a moment. Figure 10.2 is right here. Okay, so we're imagining a cell that's shaped like a cube. Alright? Sounds okay. If this cell has a length of 1 centimeter, its surface area would be equal to the length times the width times the number of sides, or 1 centimeter times 1 centimeter times 6 is 6 centimeters cubed. The volume of the cell would be equal to the length times the width times the height, or 1 centimeter times 1 centimeter times 1 centimeter is 1 centimeter cubed. To obtain the ratio of the surface area to volume, divide the surface area by the volume. In this case, the ratio of surface area to volume would be 6 to 1. 6 to 1. So let's look at our picture. And basically it's saying for the small one, the surface area is 1 centimeter times 1 centimeter times 6 is 6 cubic centimeters. That's how much space is on the outside of the cell. Or another way of saying is, if you were to wrap this up with wrapping paper, how much wrapping paper it would take to cover the whole thing. The volume is how much space is on the inside, is in the cube. So in this case, it's length times width times height, and so that'd be basically how big the box is. I mean, how much you can fit in the box. So in the ratio says that you have basically 6 cubic centimeters for every one. You have 6 square centimeters for every 1 cubic centimeter in this cell. A surface to area ratio. Basically, there's a lot of surface area, and there's a lot of surface area compared to every unit of volume. Alright? And that makes sense. Look at all the surface area compared to how much volume there is. Now let's keep reading. If the length of the cell is doubled, what would happen to the cell's surface area compared to its volume? The cell's surface area would be equal to 2 centimeters times 2 centimeters times 6, 24 centimeters. Well, look, that's exactly what they're saying. To find the surface area, you multiply this side times this side, and that gives you the surface area of one side, and then you multiply it times 6, because there's 6 sides of the cube. You get 24 cubic centimeters. Alright, but what about the volume? And then it says, the volume would be equal to 2 centimeters times 2 centimeters times 2 centimeters, or 8 cubic centimeters. The cell's ratio to surface area, the cell's ratio of surface area to volume would be 24 to 8, or 3 to 1. And that's really important. Check it out. Even though the length of the cell only increased by 1 cubic centimeter, the ratio of surface area to volume is half as much. Wow. Basically, you have 3 units of surface area for every 1 unit of volume. Less surface area for volume. Let's keep reading. What if the length of the cell triples? The cell surface area would now be 3 centimeters times 3 centimeters times 6, 54 square centimeters. The volume would be 3 times 3 times 3, which is 27 cubic centimeters. The ratio of surface area to volume would be 54 to 27, or 2 to 1. Okay? Alright? So basically, the cell's getting bigger, and the ratio or the difference, is getting smaller. In the small cell, you had lots of surface area, 6 times the surface area as the volume. Here you've only got 3 times the surface area to the volume, and here you've only got 2 times the surface area of the volume. What's that mean? That means that as you get bigger and bigger, there's more space inside the cell than there is a surface or covering to the cell. Another way of saying it is, the bigger you get, the less wrapping paper you would need to cover the same amount of volume. All right, let's keep reading. Note that the volume increases much more rapidly than the surface area, causing the ratio of surface area to volume to decrease. The decrease creates serious problems for the cell. To use a town analogy again, suppose that the small town has a 2-lane main street. As the town grows, more people will begin to use this street. The main street leading through town, however, has not increased in size. As a result, people will encounter more traffic as they enter and leave the town. A cell that continues to grow larger would experience similar problems. And that's basically what's happening here. Yeah. Let's keep going on. Please move on to the next video, page 243.